Hey there guys, and welcome to my second part video on related rates. The first part just kind of talked about what related rates were and how you take the derivative of certain geometric formulas and the Pythagorean theorem so that way you could use them in a related rate problem. And that's what we're going to be taking a look at in this video, is how to actually use those skills of taking the derivative of the geometric equation for area or volume or whatever it is, and apply it in terms of time so that way we can solve for specific things. So a related rate problem really isn't going to be that much different than what you've done in other word problem type questions in a math class, but it's going to be a little different in the fact that you definitely have to be able to take the derivative of a function or an equation and then be able to kind of plug and chug or algebraically manipulate the equation to get what you are trying to solve for, whatever particular problem that you have. Here we have a basic explanation of related rates. The derivative dy dx of a function is its instantaneous rate of change with respect to the variable x. We're going to be applying these things generally as they relate to time. When a function describes either position or velocity, its rate of change is interpreted as velocity. Remember, the velocity function is the first derivative of the position function, and the acceleration function is the second derivative of the position function. So here, that's why it's talking about how fast a quantity is changing. If v is volume that is changing in time, then we would say dv dt is the rate, or how fast the volume is changing with respect to time. The last two things here are talking about how an object relates to a fixed point. If you are walking towards a fixed point, then the distance between that point and you is decreasing. So that's why we have a negative 3 feet per second there. And if you are walking away from a fixed point, then the distance is increasing, which is why it is a positive in the second or in the last example at the bottom. Now pay attention how they're including the units. If you're given units in the problem, you better have units in your answers. Here are just some general guidelines of what to do when it comes to solving a related rate problem. Often it does help to have a sketch. It's not necessary, but it can be useful in helping you formulate a problem-solving strategy. As with every word problem or problem situation that you've ever seen in a math class, they're always going to give you just enough information to actually answer the question. So they're going to give you some things in the problem. Maybe it's a length, a height, a volume, an area, and based off of that, we're going to either be given an equation or understand that an equation that we need is a pretty common one. It should be known to us at that point. And figure out what is it asking us to find. Is it asking us to find a length? Is it asking us to find a rate? You just have to look at the problem and see what is it going to be for this particular situation. Here down on step 4, where it's talking about the chain rule, I know we haven't explicitly talked about the chain rule. We've mentioned it in a previous lesson, where we would say the chain rule is because the chain rule is when we are essentially looking at a composite function. So the chain rule says we're going to take the derivative of the whole thing, and we're going to multiply it by the derivative of whatever's on the inside part. So if I have some function that is f of g of x, then its derivative would be found this way using the chain rule. And we'll get to the chain rule, don't worry, I promise we'll get there. Now, once you get through step 5, or step 4, and you get to step 5, that's where you do your plug and chug, where you either rearrange your equation to get the thing you're looking for isolated, or you just start substituting values that you know into whatever equation that you have and work from there. So let's take a look at the first example. Suppose x and y are both differentiable functions of time and are related by the equation y is equal to x squared minus 3x. Find dy dt when x is equal to 3, given that dx dt is equal to 2 when x is equal to 3. So we have our first problem where I'm going to say y is equal to x squared minus 3x, and that was given to us. That's some information that we didn't have to figure out. So I'm going to differentiate this particular equation. Now, we are not going to try to say it as y prime is equal to 2x minus 3. That's not how we're going to express a differentiated equation for a related rate. We need to show what we're doing in relation to time. So the derivative of y, instead of saying y prime, I'm going to say dy dt. And we are going to use the power rule on the polynomial, so I do have the 2x as the derivative, but we're also going to have it in relation to dx dt. And this is kind of what they're referring to when you say the chain rule, but you do enough of these problems and it's going to kind of become second nature. So the derivative of the negative 3x is just negative 3 times dx dt. So that's the differentiated equation with respect to time. Now, what it's asking us to do, it says find dy dt, meaning that's what we have to get by itself, and that's what we have. We have dy dt by itself. Now, when I'm looking at this using proper function notation in calculus, or proper notation for a related rate problem in calculus, what we would say to find dy dt when x is equal to 3, we would say it, let me pick a different color here besides blue. Find dy dt when x is equal to 3, we would show it like this: dy dt such that x is equal to 3. And now we'll go ahead and start plugging and chugging what we know. We're given the value of x to be 3, so I'm going to have, we'll just go ahead and put our equal sign here and show that we're going to start evaluating it. So I have 2 times x is equal to 3, so I substitute a 3 for the x. And it also gives me dx dt is 2. When that dx dt is equal to 2 when x is equal to 3. So the dx dt, I'm going to replace that with a 2 here. And I'm going to say minus 3, and the dx dt again gets replaced with a 2. So what we're looking for, the derivative of y with respect to time when x is equal to 3 is 6. And that's kind of what we're going to be looking at. Now, again, here there's no diagram to draw. There's nothing for us to kind of help us with the problem-solving situation other than what they're just blatantly giving you in the problem. They give you the function that you need to be able to differentiate. They're telling you an x value. They're telling you the rate at which x changes with respect to time, and to find the rate at which y changes with respect to time when x is equal to 3, and that's how we set up and solve this particular problem. And you can work a lot of the other geometry type problems that we're going to see in this lesson without doing or without having to draw a diagram and clearly identifying what do you know, what was given to you, etc. But that's how they're set up, so that's how we're going to do them, or that's how I'm going to do them. A pebble is dropped into a calm pond, and it's rippling. So you drop a rock into a still body of water, and you're going to see concentric circles as the waves propagate away from the center of the center of the circle wherever you drop the rock. Okay, and the radius of the outer ripple is increasing at a rate of 1 foot per second. Well, here, there's your key word. First of all, they're talking about the radius, and they're telling you that the rate of the radius is 1 foot per second. So that's given information. That is dRdt. The radius changes at a rate of, with respect to time, nope, sorry, it's equaling 1 foot per second. So that is second. There's our rate. That's the rate for the radius. When the radius is at 4 feet, so there's another bit of information that we're going to be able to use. That's probably something that we'll substitute into the problem. At what rate, again, there's your word, at what rate is the total area? So that's what we're asked to find, the rate of the area. So here I'd say the rate of the area with respect to time. And in this case, they're showing us when the radius is equal to 4 feet. Okay. Well, here, what do we know? They didn't really tell us an equation that we have to use, but we're talking about an area, and we know it's going to give us a circle. So here we're talking about area of a circle, which is just pi r squared. So I hope we remember some of our geometry formulas, because we are going to be needing them here. So let's go ahead and differentiate the given equation. So I'm going to say dA dt, the derivative of the area with respect to time, or the rate at which the area changes with respect to time, is equal to, and here I would get 2 pi r dr dt. And there's our differentiated area formula. And at this point, it's really just a plug-and-chug exercise. Once you have the equation and you know the information that you're looking for. So we're trying to solve for dA dt, and it's already by itself, so we'll just leave it there, dA dt. Here we have 2 pi, you can think of that as a constant. The radius is when the radius is 4 feet, and dr dt was given to you to be 1 foot per second, so I'm going to just substitute a 1 in there. So here, dA dt would be 8 pi. Now I didn't put my units in the problem, but understand that we're talking about area, and they gave us area to be in feet. So here it would be 8 feet squared per second. Well, the pen doesn't want to write my C's. And there we go. That's the final answer for this particular problem. Now moving on to the next one. The example here is there's a little bit of typo compared to what you have in your notes and what is here. For instance, here it's telling you air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Well, in your notes, if you're actually using the handouts that I'm providing in class, here the rate is in, oops, and let me turn my pen on. The rate here, and that's going to bug me having that outline there. Go away, outline. There we go. Sorry, I just know myself it was going to bug me. 4.5 cubic feet per minute. So instead of 4.5 cubic feet per minute, we have 800, cubic centimeters, and it's per minute. Okay, so we're still per minute. So let's erase this. And we're still cubic because we're talking about volume, obviously. Air is being pumped into a spherical balloon at a rate of 800 cubic centimeters per minute. Find the rate of change of the radius when the radius is 2 feet. And what it's telling you in your notes, it's not 2 feet, it is 30 centimeters. So 30 centimeters. So So again, I'm not sure why we have the difference, the discrepancy in the values and the lengths, but it's fine. So what do we know? We're dealing with volume, and it's a spherical balloon, so volume of a sphere is volume is equal to 4/3 pi r cubed. Did they give us anything? Sure, they gave us a rate. We have a rate of 800, so this would be a rate of cubic centimeters, so that's the volume. So they're giving us the rate dV dt, the rate at which the volume is changing with respect to time. They're giving us that to be 800 centimeters cubed per, what was it, minute? Okay. So what do we have to find? Find the rate of change of the radius. So the rate of change of the radius, that would be dr dt, the rate of change of the radius with respect to time. And in this case, we're trying to evaluate it when the radius is equal to 30 centimeters. So we've established what we know. We're dealing with volume, so there's our volume. They gave us a rate, and the only variable that we really have besides volume is the radius, and they're giving us a value of the radius that we're going to be looking at. So I think we have enough for plugging and chugging, but first we need to differentiate the volume formula. So here I'm going to say dV dt, the rate of change of the volume with respect to time. In this case, when I use the power rule for 4/3 pi r cubed, that's going to simplify to be 4 pi r squared times dr dt. So they gave us the volume, the rate, so I'm going to put my 800 here. We have 4 pi, the radius was given to me to be 30, that's where we're evaluating at, and that's squared, and we're looking at it for dr dt. We're trying to solve that. Now, I could have looked at it as a literal equation and just divided everything by 4 pi r squared to get dr dt by itself, but because dV dt is already a fraction, I'm not keen on having fractions over fractions, if I can avoid it. So 800 is equal to, so what we have, 900 times 4, that would be 3600, pi, 3600 pi times dr dt, and my screen is jumping around here, dt. So that'll give me, when I divide 800 by 3600 pi, the 800 over 3600, that's going to simplify to be 2 over 9 pi, and in this case, dr dt, that's going to be just a length, so that would be centimeters per, what are we doing, minute, to be equal to dr dt. And there we go. I know, I make it look easy. No, I'm just kidding. But that's all there is to it. I mean, you've been doing problem-solving skills with math classes your whole math careers, your whole math lives. Like I said, they're always going to give you enough information to be able to work out the problem. It's just a matter of identifying what the correct information is, so that way you know where to substitute it. And in this case, the added step for the calculus tie-in is the differentiation. So moving on, here, if you feel like trying to work this one out ahead of me, by all means, go ahead, try it. I definitely encourage you to do it, but we're moving away from so we've seen a circle and we've seen a sphere as far as geometric shapes, but here this one's not going to be a geometric shape so much as something else that we do in geometry with triangles. The top of a 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. So again, here there's our keyword rate, and what is that rate? 3 feet per minute, and it's going down. So that means that 3 right here needs to be a negative number because it's moving down. When the top of the ladder is 7 feet from the ground, what is the rate? Again, so here, keyword rate of change of the distance between the bottom of the ladder and the wall. Okay, so here, the way that this would look, and I actually use an assignment, an investigation similar to this to actually kind of introduce related rates in geometry sometimes. So let's see, we kind of have our building, I guess. We got our little building here and made up of a bunch of bricks or whatever. There's your building. And we have a ladder leaning up against it. And I didn't get my, there we go. So this is 25 feet. The ladder is 25 foot. So that's always going to be the hypotenuse of the right triangle. And we're moving down at a rate of 3 feet per minute. So we're moving, here, I suppose I should have, sorry, I had I don't know exactly when it paused recording, but I went to go hit my eraser just as soon as a notification popped up in the Google Classroom, and it tried sending me to the Google Classroom. Anyway, I'm going to just erase the lines there so to show that we're going down at negative 3 feet per minute, and that's a very slow drop, 3 feet per minute. Because you think once the bottom of that ladder goes out enough, then the rate that it's going to go down is going to kind of increase. But anyway, and we're looking for this bit here. The distance from the bottom of the ladder to the wall is going to be 7 feet. So here's where the diagram may be helpful for you to identify, well, what are some things that we have to work with. So in this case, because we're working with a right triangle, that means that we're going to be working with the Pythagorean theorem. Now, here, I'm not going to do the a squared, b squared, c squared of the Pythagorean theorem. I'm going to use x and y for the horizontal and vertical, and the diagonal, the hypotenuse, I'm going to say that's z, because that's pretty typical if you're looking at it. It's just something that we do in calculus when we're thinking of horizontal and vertical. If you want to keep it as a, b, and c for the Pythagorean theorem, you're more than welcome to. You'll get the same answer either way. So I know the Pythagorean theorem would be x squared plus y squared to be equal to z squared. And in this case, z is 25, so let's go ahead and just swap that z out, and let's just put 25 there. Or z squared, I guess. It really, one of those things, because we're going to have to substitute the 25 in at some point. We're given a constant rate moving down, so that's the moving down, that would be the y-axis. So we have dy dt, in this case, because we're moving down, to be negative 3, come on, write a 3, negative 3 feet per minute. And what it's asking us to do, it says, what is the rate of change between the bottom of the ladder and the wall? Well, that would be along the x-axis, so it's asking us to find dx dt. And I don't think that, they're just giving it dx dt when it's when the top of the ladder is 7 feet from the top of the ladder is 7 feet from the ground, so that would be when y is equal to 7. Okay, so we need to differentiate the Pythagorean theorem, the a squared plus b squared, or in this case, x squared plus y squared. So let's go ahead and try doing that. Let's go ahead and differentiate this. So x squared will be 2x dx dt plus 2y dy dt, and the 25, and I should have had a squared there, I didn't square it. The derivative of 25 squared is just going to be 0. So that's what we have for that. And if you want to, you could, on the left side, you could factor out the 2, but I'm not going to do that. So let's see, do we have at this point anything that we can substitute? Well, what are we looking for again? We're looking for dx dt. So we may want to go ahead and try to get that by itself. So I'm going to go ahead and get dx dt by itself. So that would be 2x dx dt equals negative 2y dy dt. And when I divide here by the 2x, that's going to give me dx dt to be equal to, that would be negative y over x dy dt over dx dt. I know earlier I said I try to avoid fractions over fractions, but here I figured I'm going to go ahead and try and get dx dt by itself first, so there you go. Now, I know the x value, when the ladder, or no, I don't know the x value. I know when the top of the ladder is 7 feet from the ground, so I mislabeled that in my diagram, so I need to change that. That's not 7. This here is your 7 feet. So that's the y value. And we have a y value. We have dy dt to be negative 3 feet per second. And oh my Lord, I feel like such a dummy. I feel like such a dummy. I divided by dx dt when I'm trying to solve for dx dt. So here I have dx dt to be equal to negative x over y dy times dy dt. There we go. And God, I am a dummy. Look at me. I can't get anything right today. Y over x. There we go. Golly. I'm just making sure you're paying attention. That's all. So that's what we always say. Now, all right. So I have a value for y. I have a value for dy dt, but I don't know x. But the thing is that I can get x using the Pythagorean theorem. So let's just go ahead and clear off this diagram here because I don't have space for it anymore to do what I need to do. Let's go ahead and find x using the Pythagorean theorem. So here I'm going to say x will be equal to, in this case, the square root of 25 squared minus, and we have a y value of 7 squared. So 25 squared minus 7 squared. I've made enough mistakes. I don't want to do this one in my head. Square root 25 squared minus 7. I can't even type anything on the calculator correctly. Minus 7 squared. There we go. And I get a 24. So 24. So now we have enough information to plug everything in that we need to. So dx over dt, or dx dt, is going to be equal to, what do we have? Negative, and I'm going to substitute a negative, or not a negative 3. The y value is 7, the x value is 24, and dy dt is negative 3. There we go. So the 3 and the 24, that's going to simplify to be an 8, and negative times negative is going to be positive. So that means dx dt is going to be equal to a positive 7/8. And because we have our unit, we need to include it in our answer, feet per minute. Okay, wow. And that's not even the hard triangle problem for this set of notes here. But anyway, I knew together we can do anything. All right, let's move on here. This one is the triangle problem that's a real beast to try and, really explain or even understand for some people. And on this one, a diagram is really going to be helpful. So at noon, ship A is 150 kilometers east of ship B. Okay, so here, let's go ahead and get some things working here. Here's B, and here's A, and the distance between them is 150 kilometers. All right. Ship A is sailing west, so ship A, let me grab this thing here and let me kind of shift it up a little bit. So I can't speak. Ship A is going west, so it's going to be going left, and ship A is sailing, and it's giving us a rate of 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. So let's say this one is going up at 25 kilometers per hour, and this one is going west at 35 kilometers per hour. How fast is the distance between the ships changing? Well, the distance between the ships, as you can imagine, as B goes up and A goes to the left, the distance between the ships is going to become that hypotenuse between the two legs of a right triangle. All right, so what do we know? Again, we are working with a Pythagorean theorem, so let me get out of this green. The dark color is bugging me right now. So we know that Pythagorean theorem, x squared plus y squared is equal to z squared. And in this case, we definitely don't know what z is, unlike the latter problem that we saw in the last example. And now in this case, as ship A travels to the left or west, that distance is decreasing, so I have to subtract x there. All right, and so that means I could substitute that expression. I can substitute the 150 minus x squared plus y squared equals z squared. All right. They gave us a couple of rates. They're giving us dx dt of ship A to be, in this case, 35 kilometers per hour. So 35 at some point, my head's going to be back in the game. 35, and I'll be able to write all the numbers that come out of my mouth. Kilometers per hour. And they're giving us dy dt to be 25 kilometers per hour. And how fast is the distance between the ships changing? So the distance between the ships changing, that is that's a rate. And in that case, this is z, so it's asking us to find the rate of change of the hypotenuse, or the distance between the ships, over time. And in this case, changing at 4 p.m. So here we'll say when time, so between noon and 4 p.m., that would be 4 hours. All right. So let's take a look and see what we know. When time is equal to 4, what do we know about the rates? How far have they gone? Let's see. So let's look at this one here. Look at this one here in black. So if they're traveling 35 kilometers per hour, so at time equals 4 hours, then for the ship A, so we'll say here we're looking at A, at time is equal to 4 hours, then they would have gone 35 kilometers times 4. That is going to be 140 kilometers. So that means there's from where they started at 12 o'clock to where they're at 4 o'clock, then they have gone 140 miles, meaning that they only have 10 miles left of distance to change. So again, the distance from A to B as A goes to the left or west, that number is decreasing. That's why I'm keeping it as a negative number. But from if it's traveled 140 kilometers when it was originally 150 kilometers away, that means there's only 10 kilometers left before ship A gets to where ship B started at. All right, so let's do the same thing for B. Let's do that one here in pink. So for B, again, at time equals 4 hours, that would be 25 kilometers per hour times 4 hours, so that would be 100 kilometers. So here, this is 100 kilometers, and because the distance, that one's going to be positive because the distance from where it started to where it's going is increasing. Okay? So now I have, let's see, what's a good color here? Let's go orange. I have a value for the vertical. I have a value for the horizontal. So that means I can use the Pythagorean theorem that after 4 hours, I can find the value of the hypotenuse at time is equal to 4 hours. So let's do that real quick. So here, z is going, the hypotenuse is going to be equal to the square root of, let's see, the x value was, in this case, 150 minus x squared, plus the y value, which in that case was just 100. That was, you know what? Hold on a second. I want to double check something real quick. Yeah, that's what I thought. My idiot brain is still running rampant. Let's turn my eraser on for one. Come on, eraser. Let's change that. That doesn't make any sense to plug that in that way. So we have negative 10 for the x value squared plus 100 squared for the y value for the Pythagorean theorem. So here I'm going to get 100 plus, and 100 squared is 10,000. So that is going to be, I don't want to combine those because those are both factorable by 10. So 10 would be 10 plus 100. No, I'm sorry, it's factorable by 100. 100, so that would be 1 plus 100, like that, and now I have a perfect square of 100 that I can take the square root of, so that'll be 10 square root of 101. So there's your value for z. 10 radical 101 kilometers. I have no idea what that is. I'm just doing all this stuff in my, without a calculator, and so far not suffering seriously as a result of it. Okay. So now, what it's asking us to find is we have to find dz dt. That means we have to take the Pythagorean theorem and we have to differentiate it at some point. So let's go ahead and differentiate the Pythagorean theorem. So that will be 2x dx dt plus 2y dy y dt equals 2z dz dt. And the dz dt, the rate of change that we're looking for at 4 hours, that's what we're trying to solve for. So here we can start plugging some things in, and I'm going to go ahead and see if I have space to. I think I'm going to have to erase some of the Pythagorean theorem work. Because I'm running out of space here. So we know that z is, trying to select it, and it's trying to select all way more than I want. 10 radical 101 kilometers. Okay, so let's see. I want to go back to my gray. So let's start plugging and chugging and see what we get here. So x in this case is the negative 10, that the distance is decreasing. Dx dt was the 35 kilometers per hour, plus 2. The y value at 4 hours was 100 kilometers, times dy dt, which would be 25 kilometers per hour, equals, here, and I'm squeezing the space here, 2 times 10 radical 101 dz dt. All right, so let's see what we get. Let's see, negative 350 times 2. That's going to be, what, negative 700. let's see, 50 times 100? No. Oy. Let me double check. My mind's going blank here. 125. 5,000. There we go. That sounds about right. And let me just double check my first number. 2 times 35 times negative 10. 2 times 35 times negative 10. Okay, negative 700 is right. And so that's going to give me plus 5,000. And let's just go ahead and simplify that, because again we're running out of space here. So that would be 4,300 is equal to, and that would be 20 radical 101 dz dt. So now we divide 4,300 divided by 20 radical 101 equals dz dt. And this would be far enough that we would need to go really for a numerical answer on a free response question, because we don't need to simplify it. But let's go ahead and simplify it. So 4,320 are going to simplify to be 215. So that would be 215 over radical 101 to be equal to dz dt. And when I rationalize that, since we are simplifying here, I guess, I would say that would be 215 radical 101 over 101. And 215 and 101 don't simplify. And so that would be kilometers per hour to be equal to dz, the rate of change of the distance of the ships in respect to time. There we go. So my brain's not working too great right now. I had to use a calculator to help me do some basic arithmetic, but everybody needs a little help now and then. And this one's a booger. I don't like this problem. I mean, I do, but I don't. I mean, I like it in how with its depth and complexity, but man, it's a kind of a beast to try and work out. And I think there's one of those on your homework assignment. So here, I'm going to go ahead and ask you to go ahead and pause the video, and I'm going to work this one out. I want you to pause the video and try to see, can you work this one out? Because here with the right cylinder, I really don't think it's going to be too difficult for you based off of the first couple of examples that I did for you. So go ahead and pause the video and work this one out, and when you hit play, I'll have this stuff worked out for you. So see you in just a sec. All right, here it is. How does your work compared to mine? So the no stuff, again, that's kind of the formula or equation that we're working with. They're giving you the rate of the radius decreasing at -2 inches per second, and the height is increasing at 5 inches per second. And when the radius is 4 and the height is 6, what is the rate of change of the volume? So we need to use the product rule to differentiate the cylinder equation. So that's how I'm getting the 2 pi RH dr dt plus pi r squared dh dt. We're just using the product rule. And once I've differentiated it, then I just plug the numbers in that we were given. So the first part of the equation gives me a negative 96 pi, and the second part a positive 80 pi, for a total to show that the rate of change of the volume is decreasing at negative 16 pi inches cubed per second. So how'd you do? Hope you did great. I believe in you. I think you guys are all going to be wonderful at doing this stuff. So let's take a look here, see how many more of these we have to do. I think this is our last one, but this is a good one here because what we're going to see on this one is really a good exercise in how we need to analyze some of these problems. Okay, so let's scoot that down just a little bit more so we have some space to see everything and some space to write. Okay, so an inverted cone is leaking water at a rate of 1 centimeter cubed per minute. So we're dealing something with volume. The cone has a height of 9 centimeters and a diameter of 6 centimeters. Find the rate at which the water level is dropping when the height is 3 centimeters. So first of all, what is an inverted cone? Well, an inverted cone is going to kind of, it's like an ice cream cone. And that's where we have the circular base up top rather than at the bottom. So the cone has a height of 9 centimeters and a radius of 6 centimeters, and find the rate at which the water level is dropping when height is 3. So what do we know? So we know the volume of a cylinder, or I'm sorry, a cone is 1/3 pi r squared times the height. So the rate at which the water level is dropping, that means we're looking for dH dt. We're looking for the rate of change of the height with respect to time. And we're looking at it when the height is 3 centimeters. So what did they give us? The rate of change, so they gave us dV dt to be, and because it's leaking water, it's losing 1 centimeter cubed per minute. And it's also giving us the height and the diameter. But that's the really important stuff here. So let's go ahead and first, again, see if you can go ahead and differentiate the volume formula and see what you come up with. So here, that's going to give me dV, capital V for volume, dt. So here, again, we're going to have to use the product rule for the two variables that we have. So I'm going to just kind of think of the 1/3 pi as a constant, and that's no, I don't want to do that. So now we just have the r squared, so it would be 2, oops, sorry to turn my pin back on, 2 r h dr dt plus r squared, and the derivative of height is just 1, so that would be dh dt. So there's our product rule. We're just treating the 1/3 as a that'll be a constant factor that would be distributed to both of them. So let's see what we know. They gave us dV dt to be -1. So we have 1/3 pi. Let's plug some things in, and we're looking for dH dt. So all right, let's see what it looks like when we plug some numbers in. So 2, the radius. Ooh, I forgot my radius, didn't I? Well, the radius isn't changing, just the water level is dropping. So that was 6. The height of the cone is still what do we have there? The height of the cone was 9. Oops. dr dt is given to you to be nothing. We don't know what dr dt is. So dr dt plus r squared, so that'll be 6 squared, and dH dt is what we're looking for. dH dt. So differentiating the function as it's given to us is a little difficult, and that's kind of the idea for these cone problems, and we're going to see what this is going to look like here in just a second. Well, let's see. The volume formula has those two terms. It has the radius and it has the height. And inside of the cone where we have our water level, so let's say our water level is here. Well, it's dropping over time. And so what's happening is we kind of have a right triangle that we can look at inside there between the segment that represents the height and the segment that represents the radius. And what we're looking at here is really going to be, oh man, I totally messed it up. That was diameter, not radius, so that's 3. So that's definitely wrong. That's definitely wrong. So this is 3, and this height is 9. But as the water level drops, this is still the radius and this is still the height. And what we're looking at here is essentially we just have two similar right triangles. So what I'm going to look at is I'm going to say the radius over the height is equal to the radius over the height. And I can solve that proportion in terms of the height or in terms of the radius, so that way I can have something that I can come back here and substitute and hopefully simplify the problem a little bit. Because trying to differentiate the volume formula with what we had, we don't know the rate at which the radius is changing, and we don't know the rate at which the height is changing, so we can't really work the problem just differentiating the equation as it was given to us. So here, let's solve this in terms of the radius. So this would be, when we solve it, this is going to be h over 3 to be equal to the radius. And so I can take that and substitute it in here. So h over 3 for the radius. So let's clean all this stuff up, since we know we can't use it now, because there's too many things that we can't see. The rate of change of the radius, the rate of change of the height. So let's take the problem now, and volume was equal to 1/3 pi, and we're plugging in, let's see, what was it, 1/3 height, height over 3 squared times height. So let's just simplify this before we try to differentiate it. 1/3 pi, and so that would be h squared over 9 times height, times height. So volume would be, let's see, h cubed pi over 27. And that I think I can differentiate, especially because we only have the one variable on the right side and the one variable on the left side. So let's go ahead and differentiate that. So that'll be dv dt on the left side. And so here, the pi over 27, again, you can just think of that as a constant. So that'll be 3. I'm really looking at the h cubed. Here, let's clean it up just a little bit so it's easier to see. We can look at it as pi over 27 times h cubed. So I'm using the power rule there, and I'm going to multiply by 3. So it'll be 3 over 27. So that'll be pi over 9 h squared dh dt. And now we have this works a lot better, because now we know the derivative, or the rate of change of the volume, is -1, and here we're going to have pi over 9, and the height is, when we're asked to evaluate it, is at 3, so that's 3 squared, and dh dt is what we're looking to find, dh dt. So here, 9 and 3 squared, those are going to just simplify to be 1. So divide by pi, and that'll give me -1 over pi. And in this case, the height, that would just be centimeters per minute, to be equal to the rate of change of the height with respect to time. So I know this one took a little bit of time, but I wanted to try to differentiate the volume formula with the given information, just to show that there wasn't enough information for me to actually use it. That's why I wanted to go back and look at the drawing to recognize that I do have similar right triangles that I could solve a proportion with to substitute for one of the two variables in the volume formula. And that's all the examples that we have right now, and there's really not going to be a ton more of things to do. I mean, I could keep going and give example after example after example, but these are a lot of similar to word problems. I can't just do a small amount of word problems and say, okay, now you know how to do everything. You do have to take a problem-solving strategy to it, and what do you know? What can you substitute into it? How can you simplify it and do some algebraic manipulation to find your answer? Of course, now with the addition of differentiation. So anyway, thank you guys again. I'm sorry for the length of the video. I really do try my best to work through them as quickly as possible, but hope you are all doing well. Take care, be good, and I will see you in class soon.